This this diagram, it shows the second non-optimality case of the EDF and LST scheduling algorithms, where we are trying to schedule the jobs on more than one processor for execution. So here we are having two processors P1 and P2, and we are having the jobs J1, J2 and J3. And if you are blindly following without any preemption, without any proper ordering, then J3 it is missing its deadline in diagram A. Whereas while we are following a different kind of scheme, which is not an EDF or LST, in diagram B, that is in diagram B, as shown in diagram B, we can see that all the jobs, they are meeting their deadline. The next topic, it is challenges in validating timing constraints in priority driven systems. The timing behavior of a priority driven system, it is non-deterministic when job parameters vary. So it is difficult to validate that the deadlines of all jobs scheduled in a priority driven manner, they are obtained or attained. So what we need to worry about, the challenging thing, it is a validation problem. And validation problem, it can be stated as follows: given a set of jobs, the set of resources available to the jobs and the scheduling algorithm to allocate processors and resources to the jobs determines whether all jobs meet their deadlines. So this diagram, it shows the anomalous behavior of the priority driven systems. So what is anomalous here is, in diagram B, so here we are having two processes P1 and P2, and we are having the jobs J1, J2, J3, J4 with Ri their release times, Di as their deadlines, and Ei minus and Ei plus are these as their execution times. So J2, for J2 it is given differently, where the minimum execution time we can take it like 2, and the maximum execution time we can take it like 6. So these diagrams, they show the different cases of execution of J1, J2, J3 and J4, starting with the execution by taking different values of execution times of J2. So when J2 execution time it is 6, okay, all jobs, they are meeting their deadlines. When J2 execution time it is 2, then also the case it is okay. So these are the remaining two diagrams, in diagram C and diagram D. In this diagram, when the execution time of J2 it is 3, then J4 it is missing its deadline. And there is another case, diagram D, where when the execution time of J2 it is taken like 5, then the jobs are meeting their deadlines, so the case is safe. So the difference in the achievement of deadlines of these jobs, due to the varying execution times, it is the anomalous behavior of priority driven scheduling. Predictability of executions. The execution of job J under the given priority scheduling algorithm is predictable if the actual start time and actual completion time of every job are bounded by its start times and completion times according to the maximal and minimal schedules. Let S plus of j and S minus of j be the start times of ji according to the maximum schedule and minimal schedule of j respectively. These start times can easily be found by constructing the maximal and minimal schedules and observing when ji starts according to the schedules. We say that ji is start time predictable if the following thing is achieved, or if the following thing is okay with job ji. So what is the thing that is to be maintained is S of ji, the start time of ji, it is having a bounded time interval, where it's the minimum boundary it is S minus of j and the maximum boundary it is S plus of j. Similarly, we'll have the feasible schedule for a set of jobs ji, where there is a for the feasibility of job ji, there is a minimum boundary and maximum boundary. The minimum boundary it is F minus of ji, and the maximum boundary it is F plus of ji. The execution of ji is predictable, or simply ji is predictable if ji is both start time and completion time predictable. Theorem 4.4, it is stated like this: the execution of every job in a set of independent preemptible jobs with fixed release times is predictable when scheduled in a priority driven manner on one processor. Next topic, it is validating algorithms and their performance. A validation algorithm allows us to determine whether all jobs in a system indeed meet their timing constraints despite scheduling anomalies. A validation algorithm is correct if it never declares that all timing constraints are met when some constraints may not be. The merits of validation algorithms are measured in terms of their complexity, robustness, and accuracy. A validation algorithm is good when it achieves a good balance in performance according to these conflicting figures of merit. Every rigorous validation algorithm is based on a workload model. A validation algorithm is said to be robust if it remains correct even when some assumptions of its underlying workload model are not valid. Efficiency and robustness can be achieved easily if we are not concerned with the accuracy of the validation test. A validation algorithm is inaccurate when it is overly pessimistic and declares tasks unable to meet their timing constraints except when system resources are unduly underutilized. A scheduler using an inaccurate validation algorithm for an acceptance test may reject too many new tasks which are in fact acceptable. Next topic, it is offline versus online scheduling. A clock driven scheduler typically makes use of a pre-computed schedule of all hard real-time jobs. When the operation mode of the system changes, the new schedule specifying when each job in the new model executes is also pre-computed and stored for use. In this case, we say that scheduling is done offline and the pre-computed schedules are offline schedules. The obvious disadvantage of offline scheduling is inflexibility. For a deterministic system, however, offline scheduling has several advantages. Competitiveness of online scheduling. Scheduling is done online or that we use an online scheduling algorithm if the scheduler makes each scheduling decision without knowledge about the jobs that will be released in the future. The price of the flexibility and adaptability is a reduced ability for the scheduler to make the best use of system resources. The system is said to be overloaded when the jobs offered to the scheduler cannot be feasibly scheduled even by a clairvoyant scheduler. A reasonable way to measure the performance of a scheduling algorithm during an overload is by the amount of work the scheduler can feasibly schedule according to the algorithm. The larger this amount, the better the algorithm. The value of a job is equal to its execution time if the job completes by its deadline according to a given schedule and is equal to 0 if the job fails to complete in time according to the schedule. The value of a schedule of a sequence of jobs is equal to the sum of the values of all jobs in the sequence according to the schedule. A scheduling algorithm is optimal if it always produces a schedule of the maximum possible value for every finite set of jobs. An online algorithm has a competitive factor C if and only if the value of the schedule of any finite sequence of jobs produced by the algorithm is at least C times the value of the schedule of the jobs produced by an optimal clairvoyant algorithm. Theorem 4.5 is stated as follows: no online scheduling algorithm can achieve a competitive factor greater than 0.25 when the system is overloaded. So this is shown by the following example. The first example, it is the thing where there is a situation when at a busy time interval with the job ji, for example if we take job ji and we take a job ji plus 1 when job ji is executing, and at the same time when ji plus 1 is also released some epsilon time before the deadline of ji, then we need to choose one of the two things, ji, the execution of ji or ji plus 1. So the two cases, they are, in the first case it is where the job ji will be preempted from execution and job ji plus 1 will be executed, and this goes on till we reach the last job in the schedule. The second case, it is the case where job ji plus 1 is preempted or omitted from execution and we concentrate only on the execution of ji till the completion time of ji. So in case 1, the total value achieved by the scheduler is Emax. In case 2, the total value achieved by the scheduler, it is sigma k is equal to 0 to I ei. The execution time ei of the ith major job is given by the following equation: ei is equal to c into ei minus 1 minus sigma k is equal to 0 to I minus 1 ek. So now if we try to find out the value of ei, then ei, it would be, in the first case, if we take this equation for the first case, then it would be 1 by c. Then the value of ei, it would be, the execution time, it will be 1 by c. And in the second case, it would be sigma k is equal to 0 to I ek. So of these two things, for the first one, okay, if we consider these two cases, then no doubt the case 1, it will be having less time or more time. Okay, it will be having more time compared to the case 2. And for that to happen, we can test such that c, if and only if the value of c, it is 4, then only the case 1, it is having a major value compared to the other case. So thank you for listening to the narration of the fourth chapter of Unit 1.